Okay, so for today's lecture, we're going to cover WhiteboxTools. So you'll be number 15 here, lecture number 15. Before we get started, how many of you have used Whitebox? Or how many of you have heard about WhiteboxTools? No one? So I guess you have never used it. And so WhiteboxTools is a kind of a processing toolbox. And I'm sure you have used ArcGIS toolbox, right? Have you used some of the tools in ArcGIS toolbox? If you have used QGIS, QGIS also have some of the processing tools. And it's very much similar, but WhiteboxTools is open source and it has over 500 tools. So you have a lot of tools to choose from. One nice thing about WhiteboxTools is free, it's open source. So if you're someone that you want to look into the algorithm, you want to have things under your control, this is a great alternative to ArcGIS Toolbox. So ArcGIS Pro has a lot of tools, but if something goes wrong, you won't be able to fix it yourself because the tools are not open source. So you cannot actually see what's the source code behind the scene. But WhiteboxTools is very powerful and it's super fast. It's much faster than ArcGIS Pro, any tools that you're going to run, because it's developed using the Rust language, R-U-S-T. It's a language that has very high performance, very, very efficient. And it's close to C language, but it's like memory safe. It's a relatively new language, so probably you have not heard about it, but this is one of the geospatial toolkit that developed using the Rust language. And if you want, you can go to the GitHub repository. So here, if you click the link, it's on GitHub, so you can take a look at the source code. These are all using Rust language, and it's developed by Dr. John Lindsay from the University of Guelph. He is the one that has developed a lot of open source tools in the past. Actually, when I was doing my PhD, I used some of his tools, and so I benefit a lot from his contribution, and that's why today I'm doing a lot of open source. It's because of him, inspired by him. And he released a lot of tools that are very powerful that you won't be able to find in other GIS software tools. And today I'm going to show you two applications, how to do watershed analysis and also how to do some LiDAR data analysis. So those are some two very common applications in GIS, right? You can delineate the watershed, you can delineate the stream network, and you can also do some LiDAR, for example. How do you create a DM from the LiDAR? How do you create a DSM from LiDAR? So we're going to get hands-on on some of those real-world applications. And it's open source. So here's a kind of brief introduction. Why do you want to do? So basically, you need to understand WhiteboxTools is kind of geodata processing. It's not a cartography toolkit. It's not about making maps. It can certainly make maps, but it's not going to be as comprehensive as desktop GIS like QGIS, ArcGIS. You can create a lot of different map layout. You can change a lot of things. This is more like in basically data processing. Makes it really, really fast. And so initially it's just a command line language, and they provide a different so-called front ends. So basically the command line is the back end, basically the executable. The front end basically is just the interface that interact with the back end. So when it was initially released, it's just the command line. So basically just like you need to open the command line, you need to know how to write those command lines. It's not very user-friendly. So I built on top of that one and created the Python front end that actually the WhiteboxTools also has the Python like script, but it's not a Python package that you can install in the past. So I created this Python front end and also the Jupyter Notebook front end, R front end, and also ArcGIS front end. So those are the four that I created on top of that one. And there's also a QGIS plugin. This one I didn't create it, but initially it's by some other community contributor, but eventually Dr. John Lindsay created his own QGIS plugin. But Whitebox also has the so-called Whitebox workflows for Python and also for Python Pro. So those are the more like latest version that created by the Dr. John Lindsay himself. But this still these are still functional. So this front end still works. And let me show you, if you're already ArcGIS user, you can also use WhiteboxTools. It's very simple. So for example, here, you can just click this link and let me show you what it looks like. So if you click, it's going to take you to GitHub repository. So this is the one that I created and created this toolbox. If you scroll down, and you might be familiar with some of this, you have used ArcGIS ArcMap in the past. It also supports ArcGIS Pro. So you look at the toolboxes. It's pretty comprehensive. So it has a lot of tools available. Right now, over 540 something. So it's tons of tools. And most of the tools are over 400 of those are open source. So you can look at the source code, how it was done. All you need is just download this one to your computer, and then just link this one, connect this one in ArcGIS Pro or ArcMap. Then you'll be able to use it just like a toolbox in here, just like any traditional ArcGIS toolbox. And it's very, very powerful. So if you want to learn more, there's a website here, WhiteboxGeo. So this is kind of the company that created on top of this open source. It's free. It's so-called, they have the open core that has 470 or 80 tools. It's all open source. But they also develop a lot of so-called extensions. So those are some of the for paid users, more advanced or latest developments. Those are not free, but you don't have to pay. If you want to support them, you can buy a license. I think for student license, it's only like 10, 20 bucks a year. So it's pretty affordable. And there are a lot of things you can do. So today we're going to just use a small subset of the tools, but you can look at some of the maps that was created, and it might be useful for some of your projects in the future. So again, you're welcome to check out the website, and if you want to use some of the official products, you can. But for today, we're going to use the free version. You don't need to pay anything, and you can do a lot of stuff. So this is about the software, and there's also the user manual. I wanted to show you here. It has very comprehensive documentation. So for every tool that we're going to utilize, you'll be able to find the help documentation from here. So it has, for example, different tools, morphometric tools, GIS, hydrological analysis, image data processing, LiDAR, even machine learning, and precision agriculture and stream network analysis. So it has a lot of tools available. And for any of those tools, you click, you'll be able to find the help documentation and also the sample script, how to use it. So for the notebook we're going to cover today, I won't be able to explain details about every tool, but you can always come to this user manual to look at the help documentation, or you can just search, use this one to do the search. You will be able to find the documentation. Okay, and so in order to run this one, you can just open this one in Google Colab, and keep that in mind. Here I want to point out, okay, pay attention. Otherwise, you're going to run into errors. So you need to install these dependencies. But after this installing all these dependencies, you will probably upgrade NumPy to 2.1, version 2.1 or something. And some of the packages actually do not work with NumPy 2.1. So you need to install this one. So basically, uncomment this one, install it, and then install NumPy 1.2.26.4. Otherwise, later when you're running some of the codes, you will run into errors. So this is something that you need to pay attention. I try my best to test all the packages, but some of those are out of my control because different dependencies require different version, and sometimes they update it by accident, and you will break other packages. So make sure that you install both of these, and then just restart the runtime. Then you should be good to go. But if you encounter any error messages, even after you follow the instructions, let me know. So hopefully in the future you don't need to do this one, but for now, this is the temporary solution that you need to do. Otherwise, you won't be able to follow through. Okay, any questions? Okay, so if not, that's I'm going to switch to VS Code. So we're going to use DiffMap. So DiffMap built on top of WhiteboxTools. So you can just use DiffMap to call WhiteboxTools. And so a lot of data set that, excuse me, going to be generated by WhiteboxTools. Some of those data set are using the node data using the integers 32-bit. So the node data will be this one, 32768. And so we're going to set this one as no data. And in this way, when we're adding the raster to the map, it's not going. You don't need to use the no data parameters all the time. It will automatically retrieve this no data from the environment variable. So we automatically make the no data transparent. So you don't have to manually set the no data. So run this one. And then let's create some interactive map here. So the first one, I'm going to create an interactive map. I'm going to load the open topo map. I'm also going to load the 3D elevation and also the USGS hydrography. Okay. So the US hydrography dataset is basically the delineate all the watershed and also stream network based on elevation data. So if you zoom in, you should be able to see these streams, rivers, and all these hydrological features. And for us, for this lecture today, we're going to show you how you can delineate something like this. How to actually create this kind of national database because they use some of the DMs. So we're going to basically create some of these similar features and compare them, see how accurate they are. So this is from the national map. Again, you can turn the layer on and off. Also, there's a 3D elevation. Oops, why it doesn't show up? Here. Sometimes the base map may not work. Anyway, so mostly we're just going to use the USGS hydrography dataset later, but right now just the base map. So first, let's download some data. So here, I'm going to add a marker. So I'm going to execute this one. And so we're going to use, basically, we're going to download a DM from sample for a certain point. So this is the point in Oregon State, okay? You can click your map, you can select any watershed. So if you ever need some data, you need some DM, you need some data set related to watershed, you can just use this map and then click a marker. For example, select anywhere on the map, for example, anywhere you like. I can place a marker maybe somewhere here, right? It doesn't have to be this location. It can be any location around the US. And then you can just select the geometry. Oh, you need to... Yeah, I'll execute this one, then the geometry. So this one, this map has this function called get WBD. WBD stands for watershed boundary dataset. Okay, so it's from the NHD, National Hydrography Dataset. So automatically, once you have the latitude and longitude, you can automatically download the watershed. So this is, for example, this is digit 10, so hydrological unit 10. So in the National Hydrography Dataset, we have unit from 2, 4, 6, 8, 10, 12, 14, 16. So basically, it's a hierarchy of watersheds. So right now, this is watershed like 10, but you can also download, for example, number 8. Let me show you the differences. So if we change this one to 8, you're going to get a larger watershed, right? So here, look at this. So this is 8. So number 10. So 10 is part of the hydrological unit 8. Okay. You can also download 6, 4, 12, different levels. So for example, I can download maybe number 4. Right. So this is another watershed. So you can think about they subdivide the entire US into a lot of watersheds with different hierarchy. And so if you need to get some data, you can specify what kind of hierarchy do you want. In this case, we just want the hydrological unit, for example, 8. So once we retrieve this one, you can save the data as a GeoJSON file to our computer. So for example, this is the area that we want to work on, okay? And because it's a geodata frame, we can save this geodata frame as a GeoJSON file to our computer. So after that, you should have this one here, basin.geojson on our computer. So this is kind of just the watershed boundary. Once you have the watershed boundary, then you can get the DM. So this one shows you, the next code block shows you how to download the DM automatically. And if you ever, in your project, any of your project, for example, for your final project, you want to get some data, you want to get some elevation model, you can use this map to get it. So the watershed boundary is this one, the geodata frame, and you can specify the resolution. So this is going to download the data from the so-called 3D elevation program. So they have elevation data from ranging from 30 meter to 10 meter to 3 meter to 1 meter. So you can download them automatically without having to go to the website. So just specify the boundary, the resolution, where do you want to save this file, and also the coordinate system, which one you want to use, and whether or not you want to convert this one to a cloud optimized GeoTIFF. And you just say yes. So the output going to return is a X-array data array. So in that way, if you need, you can manipulate the data set. And this might take some time, depends on how big is your area. But for this specific watershed, it should only take you a couple seconds. Take a look. So now we have this data array. How many rows? How many columns? And you see a lot of no data in here because it's a watershed, so it's not a rectangular area. So the boundary, you will see a lot of no data. Any errors when you execute this one? No? So now you can display the DM. So because we saved this one as dm.tif, and take a look. So now we just use diff map to automatically download the DM for this specific watershed. Again, you can do it for anywhere in the US. It doesn't have to be this location. So all you need is just a bounding box. All you need is just a geodata frame to pass into this function, get3.dm. Then you can download for whatever you like. So it can be up to 1 meter resolution, very, very high resolution. So this is just a 30 meter resolution DM. And just by simply looking at this one, can you tell me where is the high elevation and where is the low elevation? High to the right, lower to the upper left, right? So because this is just a color map. So usually the blue color, in this case, the color map is terrain. So blue color represents low elevation. The brown color here represents high elevation. So right. So the water is basically floating from here, right, and all the way down here. And there might be some river later when we're going to show some satellite imagery, but this is just a simple way of getting the DM. And so in order to basically have better visualization, sometimes you might want to see like what's the highest elevation, what's the lowest elevation. So you can get some metadata information from the DM. So you can use the image metadata. And this one I'm going to show you, for example, what's the bounding box, what's the bank name, what's the coordinate system, something like that. But it doesn't contain the minimum value and also the maximum value. So we're going to run this one, image min max. So this function is going to show you maximum value and also the minimum value, basically the maximum elevation and minimum, right? So the 70 is the minimum and 1564 is the maximum elevation. So with this one, then we can add the so-called color bar. So the color map give you like representation, so you can see what's the elevation between this data set. So we come back to here. All right, so now take a look. So we have this color bar and it nicely represent the elevation range of this watershed. So ranging from roughly 69 to almost 1500, right? From low elevation to high elevation. So that's it. Once we have the DM, now we can start doing some analysis. So this is where you can start really doing some geospatial analysis. So far this semester, we have been focusing on doing some simple data manipulation, opening the data, doing some data visualization, but we haven't really done any real geospatial analysis. And so the next section here is where we start doing some real geospatial analysis, right? So you're doing some GIS analysis, we're going to deal in the watershed. So in order to do that, we're going to use WhiteboxTools. So again, leaf map already built on top WhiteboxTools. So you can just call leafmap.whiteboxtools and then assign this one, basically doing initialization. So once you have this WBT is pointing to the WhiteboxTools. It's kind of pointing to the executable. So you can call any functions available in the WhiteboxTools. And the first one, you can check the version. So this is version 2.4. And you can also talk the WhiteboxTools GUI. So this is basically the user interface. This one actually allows you to run the tools directly within Jupyter Notebook. So it's the specifically designed for Jupyter Notebook and Jupyter Lab. So how many tools in here? You see this one? 545. So this is just like an ArcGIS toolbox. And so you can go through the source code in here, all the tools available. You can also source any tools. For example, source tools. I can source, for example, how many tools contain the keyword LiDAR? 48. Okay. And is there any other tool you want to use? For example, maybe dissolve. Okay, there's a dissolve tool, right? If you're ever using ArcGIS, right? There's a tool that you can dissolve all the polygons. And this one has you as well. You might see some black color in here. This is just the dark sim. It's some of the iPad widget doesn't work very well. But if you use Jupyter Lab, it should be better. So nice thing about WhiteboxTools is you can inspect the source code. There's a button here, View Code. If you click, it should open your browser and then take you to the source code of this particular tool. So you can scroll down here, you can take a look. There are thousands of lines of source code for each tool. And this is not something you can get using other ArcGIS desktop GIS. For example, ArcGIS, all the tools are closed source. You cannot see the source code. But this is all free. And if you're someone really into it, you can look at the source code and learn how they actually doing that. And besides that, you can see here, you can select input the dataset. You can select whatever dataset you like. You can select input, you can select output. And then you will be able to actually run the analysis using just this toolbox. So it's super easy. For example, they say, okay, I want to do some hydrological analysis and I want to fill the depression, right? I know there's a few depression tools in here. You can look at the description, okay? Fill all the depressions in a DM. Anyone know like what is a depression? It's not going to talk about the mental health, okay? Not about your mental depression. It's about the DM. The water gets stuck in the DM. So if your pixel value is lower than your surrounding, then it's called a depression. It's called a sink because the water has no, once the water gets in, it doesn't flow out. So in hydrological modeling, usually you need to fill the depression so that you can delineate the stream network, right? So if you're able, for example, notice like whenever it rains, right, on some of the roads, you will see some of the puddles, the water gets stuck in there. So those are basically like sinkholes, potholes, or depression because there's no flow direction. Once the water gets in, it's going to stuck there until the water level increase, and then eventually going to flow to the other lower elevation area. So if a pixel, its elevation is lower than the surrounding 8 pixels, it's called a depression. Okay. So in DM, sometimes we need to do this so-called pre-processing is to fill the depression. So for example, we can use this tool, and all I need, select the DM, right? We just downloaded the DM, so it's called dm.tif. I can select this one here, and then click select. Then you can select the output. So I'm going to say fill.tif, okay? And then click select, and that's it. So we select the input, select the output. The input here, if it is kind of a yellow color, that means the file already exists. If this green color, that means it's a new file. So it's going to be created. And so this is so-called field depression in hydrological analysis. So then I'm going to click run, see how long it's going to take. Okay, for this DM. Click. Boom. Done. How long does it take? 0.18 seconds. Is it fast? Have you ever used the ArcGIS and then open a toolbox and then run a tool? It's going to spinning, and then sometimes takes forever. For all the tools in Whitebox, most of the tools is like seconds. It's really, really fast and very, very efficient. So give it a try. If you ever use some of the tools in ArcGIS, and then you can find some corresponding tools in the WhiteboxTools and see how far it's going to take you. Nice thing, you can automate the whole process. But I'm just showing you this interface available. So if you want to use the interface, you are welcome to use it here. And so once you're done, I can just say close, then it's gone. So this is basically just iPad widget that built on top of the toolbox. So next, let's start doing coding. Like how do you automate the whole process? How do you use the DM to do all the data processing and then eventually delineate the stream network? So in order to do that, first let's set the so-called working directory. If you set the working directory when we are save the file output results, we don't need to specify the full path. Otherwise, you need to always like cd and blah blah. So we can just specify the file name. So for this case here, always to get wcwd, always to get current working directory. So that means where this notebook is located, all the results are going to save to this notebook under the same directory, right? So basically, I'm going to save in here under my same directory. After that, the first step we're going to do is to smooth the DM. So there's a tool here called feature preserving smoothing. So basically, you're going to smooth out some of the values by going to keep the features. And this is similar to the so-called some of the other focal statistics. For example, calculate the mean, calculate the basically the moving window, calculate the median, something like that. But this one is better because you're going to keep, if the feature is very obvious, you will keep some of those features. And so just run this one. It's going to take 1 second. So you can filter here, you can set the window size, like how big we want this, the moving window to be. So what it's doing is going to slide things through the images, and then going to take, for example, some of the Gaussian value based on the Gaussian distribution, and then going to take the value and then assign the value for at the center of the value assigned by considering the pixels in the surrounding. So basically it's just smoothing. Sometimes especially for LiDAR data, your data are going to sometimes very noisy. So you can smooth things out. And after that, let's add this one to the map. So we're going to add a setup base map. We are going to add a DM. We also get a base and boundary. Also, I'm going to show the Oh, I think I need to update the leaf map. Otherwise, you're going to see this one here. It's because I updated the leaf map so that you don't need to see the background. Do you see this one on your computer? On Google Colab? Google Colab probably installed the latest version. So I think I didn't have the latest version. So let me quickly update it. If you see this background, this is because it has no data value. And this one, I believe, is 3. Let me click this one. You see, 32,768 negative. So it's the no data value. So if it happens, you can do it this way. So I'm going to basically add raster and then no data equal to negative 3768. Unless you're seeing this background, you can specify the no data, then you'll be gone. So if I run this one again, hopefully it's gone. So now if I zoom in, you will not see the no data. So you will treat this negative 32,768 as a no data. So you will make it transparent. But it's annoying because you have to specify this one all the time. So if you update leaf map to the latest version, if you're using Google Colab, you don't have to do that. If you have installed leaf map locally in the past, then you may need to update it. So I'm going to update it quickly. Pip install -u leaf map. So hopefully after that, I don't need to specify the no data. So I'm going to restart my kernel. And then I need to import again. Make sure that you run this one. So okay, set the environment variable. So in that way, div map can automatically retrieve the environment variable. So you don't have to set it every time. And I'm going to go to the smooth the DM. So we did this part. Let me initialize leaf map and this one. And then set the working directory. Then I can run this one. So in this time, I don't need to set this no data. It should be automated. So let's see if it works. Okay, great. You see? Now I don't see like the black, green blue background anymore. So this is the DM they want to work with. And on the right here, you can turn on the USGS hydrography dataset. So if I turn this one on, do you see the stream network? You can zoom in. And nicely, you see all this stream network. You can turn the layer a little bit transparent. Maybe the DM, see this? And the watershed, you may turn this one off, turn this one, DM. So what we are trying to do here is how do we delineate this stream network by ourselves? Using the DM, just the input, just the DM. We are able to automate the process and create this one, and then we can compare to the national data set, see how good is our algorithm. Okay, so first step, we can also create a hue set, and we can add a hue set to the map. So nice. Oops. If you run those two code blocks, we should be able to have the hue set. And let me turn this one off. And the hue set, I'm going to have the, where is it? The DM, right? So it's going to look like this. Okay. So if we zoom in, can you see some of the kind of a 2.5D? It's not perfect, but you can certainly see some of this just like the terrain. So it's not compared to just the DM. It looks a little bit better. So this will be just the DM, and it's transparent. It will otherwise look like this. Okay. So right now, what we're using is we make it a little bit transparent, so we can combine different data layers together. So this is with the hue set, and this will be just the DM. Okay. And so the next step is to find some of the so-called depressions, no-flow cells. Basically, in the DM, any pixels that has values lower than its surrounding, it's going to be a so-called no-flow cell. That means if you're trying to do simulation on hydrological flow, and the water is going to stuck in those pixels, you can use this tool to figure out where they are. So if you run this one and then just add the raster, go back to the one above here, and if you zoom in, okay, do you see a lot of dark pixels? If you zoom in, so those all the pixels, that basically means that the elevation is lower than its surrounding. So those are basically where the potholes are, the so-called sinkholes or the depressions. So if you zoom in, it probably makes sense. You see kind of it's like a hole, and there are lots of this on the landscape. It's real because when it rains, you go outside, you're going to see water stuck everywhere. It's not going to be everywhere, but you're going to one here, one here, one here. The reason for that because there's a pixel with elevation lower than its surrounding. So take a look. And in order to delimit the stream network, the first step is basically to remove all these non-flow cells. So basically, you're going to raise the elevation of this non-flow cell so that the water can flow continuously. Basically, you're going to send out to fix all the potholes on the road so that it's smooth and there's no water going to stuck there when it rains. So what you need to do here, you can use this one called field depressions, and this one is going to modify the DM and raise the elevation of those non-flow cells to the minimum that is required, and so that it becomes a smooth DM. So once run this one, and in order to fill the depression, there are two ways. You can fill the depression, or you can so-called the other one called depression breaching. Depression breaching basically is not fill the DM, but just modify the surroundings, so make the surrounding lower so that the water can pass through. So this would be just like breaching, would be just like you open the dam, the gate on the dam, and then let the water flow out, right? Otherwise, you need to raise the water to the minimum level of the dam, and then the water can flow out. So there are two ways you can do the so-called fill the depression. And then if you try to find the no-flow cell again, and they should be gone. Okay, so this will be the modified DM. So basically, before we do any hydrological analysis, we need to make sure that the DM is without depressions. Otherwise, when you're trying to calculate the flow direction, it's going to be a lot of artifacts. Okay, so the analogy will be when you're going to the party, put some makeup on your face. Okay, so that you remove all the black dots or anything on your face, so that it looks good, it looks smooth. This is exactly what this is doing in here. Once right now it looks very smooth, right? Pretty nice. It's a decent DM. Now we can start doing some analysis. So what we're going to do here is that we're going to delete the so-called flow direction. So what exactly is flow direction? Flow direction means every pixel, for example here, right? Think about any pixel on the DM. The flow direction basically is the steepest direction where it's going to flow, right? So whatever the water drops on the landscape, the water is going to flow from high elevation to low elevation. Make sense? And in hydrological modeling, we're using the DM. So there are 8 surrounding pixels. So where the water is going to flow, we assume that it's going to flow to the lowest neighborhood, the steepest slope. Make sense? So just like when you are rolling from the mountain, when you're doing the skiing, right? You're not skiing upward, right? You're going skiing from high to low. And also you're going to skiing towards basically the steepest slope. So whatever is the steepest, that one is the flow direction. So we have so-called 8 possible flow direction from to the north, to the northeast, to the east, to the south. This is called 0, 2, 8. So that's kind of like if you're using ArcGIS, for example. They have a good demonstration. ArcGIS flow direction, spatial analysis, and maybe the second one. This one will be better. Okay, like this. So how it is actually determine the flow direction. So for example, this is the pixel we're trying to determine your center. And how do you figure out, for example, where's the flow direction? So for example, let's look at this one, number 67. Look at this pixel, number 67. When there's water drop into this cell, and these are all the elevation, represent the elevation of the pixel, where do you think where the water going to flow to? Most likely 44. Why? Because the lowest one, right? Your surrounding has 8 pixels. So 67, this one 53, this one is 44, right? So that means it's most likely to flow to this direction. So what is this direction? What's this direction? If you take this is the center, right? So you're going to flow to the southeast, right? So to the right is east, right? To the down here is south. So this is flowing to the southeast direction. So in ArcGIS, we have 8 possible directions, right? So from here, this pixel, so from the south to the southeast, what's the value? 1, 2, 4, 8, 16, 32, 68. So the 2 to the power of from 0 all the way to 8. So this is number 2. And look at the pixel value of this one when you calculate the flow direction. What's that? What's this value? Number 2, right? Because it's floating to the southeast. So this is how the flow direction was calculated. And maybe change to the other one. How about this one? 31 here. Where it's going to flow through? 16, right? 16 the lowest. So 16. So what's this direction? South. So what's the value for south? 4. And we come back to here. Is it 4? Yes. So the flow direction basically is going to generate, basically this is DM, and this will be the flow direction raster. So every pixel in the flow direction raster is going to be a value in one of these 8 possible scenarios. So for example, if you encounter, okay, this pixel is number 8. What's the flow direction for this pixel? Where is 8? It's here, right? So it's going to be southwest. So that means this one here, 38, is going to flow to here. Yeah, it makes sense because it's 22. This is how to figure out. So what we're trying to do is to give you a DM and you figure out where each pixel is going to flow to. It's always going to pick the lowest surrounding, okay? Whatever is the steepest slope is going to flow, we assume you're going to flow to that direction. But in reality, in the water flow, you can flow everywhere. As long as you are lower than that, the water can flow to there. But we just to make it simple, we assume that all the water is going to flow to one direction. But in reality, it's not always the case. So here we just use the simplest one, flow direction, and D8 pointer means direction, 8 possible directions. And once we have this one, we can calculate the so-called flow accumulation. So flow accumulation basically means how much water is going to come in from the upstream, right? So because every pixel is going to move to the downstream, eventually it's going to accumulate the water. Same thing, you can just do like ArcGIS. I show you the kind of the explanation. ArcGIS flow accumulation and how flow accumulation works. Something like this. So here, this is the flow direction. So you can think about from the upstream to the downstream, eventually the water going to converge. And this is for every pixel going to have a value. So if you have water contributing to yourself, then you are basically in the downstream. So you know exactly how many pixels contributing to yourself. So it's going to accumulate, in the downstream. So the value becomes larger and larger, right? And this is where the water actually converts, like where the river, all the water going to come in from high elevation to low elevation. Eventually going to fill lake, river, and then floating into the ocean. And so the flow accumulation is going to show you how many pixels from upstream flow into you, because it's going to accumulate. And let's add this raster to the map. Okay, so now we should have this flow accumulation. It should take a couple seconds to load up. Hopefully it works. Come on. And you should see a relatively dark imagery. It's very, very dark, because most of the pixels basically is only have a small number of accumulation. But do you notice something brighter in the middle? So that means those pixels basically has higher value, higher flow accumulation. You're welcome to use the toolbox to actually inspect what's the pixel value. For example, you can click this one here and click. It's kind of a not very high resolution, but it might take some time to load up. But if I click here, okay, now it opens up. So see this one, 715, 183. So that means a lot of pixels contributed to this river. If you click somewhere outside, it should be much smaller, because not every pixel contributed. For example, this one only have 11. So, and right now it's not so obvious, but usually we can set a threshold to set basically flow accumulation. So if it is greater than a certain number, we want to extract the stream. So for this case, I can just set 5,000. So if that pixel has more than 5,000 pixels contribute to it, I want to extract it. So for flow accumulation, you can also set a threshold. The smaller the threshold, the more streams you're going to extract. The larger the threshold, the smaller number of streams you're going to extract. So this is basically figuring out what's the threshold you need to set. And this function is called extract streams. After that, now I can add the stream to the map. Oops. Interesting. Oh, okay. Maybe because it's something like this. Let me remove this one. And okay, now it works. So this will be right now. Let me turn this one off. You see, so now we have these streams, but it's a raster data set, so it's not very easy to visualize. And the next section here shows you how to do vectorize, and it will show much better. So also you can calculate the distance from outlet. So you can calculate raster, for example, how far are you from the outlet? How far are you from a certain location? We can run this one, and then we can generate another raster. So this can be helpful if you're trying to figure out, for example, if you're doing some like disaster management, you want to see how far are you away from the flooded area. Then you can calculate basically the distance to outlet, how far you are from the certain point. And so next, let's vectorize and then add it to the map. So one thing you need to pay attention, because some of the tools in Whitebox, after do the data processing, it miss some of the coordinate system. So you need to call this leaf map function to add the GIS to the vector. So in that way, we can show it on the map. So let's run this one. That group. Now I have this. So this will be the stream network that we just delineated based on this DM without using anything else. And so let me turn off other data layer so that it's not it's loading a little bit faster. Oops. Not sure why it's not. Let me turn this one off, turn this one off, off. Okay. And so this is just setting a threshold. So all the lines in here are the streams that has more than 5,000 pixels contributing to it. And let's turn on this the USGS hydrography dataset to see how good it is. You need to turn this one off. And are they matching each other? Oops. Yes, it's a little bit slow. But certainly you can see they kind of very, very close. For example, let me turn this one off. You see that? The reason why we don't have those smaller streams. Why we miss a lot of smaller streams. But the major one looks pretty much similar. So what's the reason why we don't have this smaller one? For example, in here, it's because of the threshold, 5,000. If you say like 500, you're going to get a lot more. Make sense? So you only extract the larger one, any pixel greater than with 5 threshold 5,000. But you can certainly see that this is how they delineate it using the same DM, the same techniques. It might be slightly different, but overall, this makes a lot of sense because this is how they delineate it. And another thing you can do is actually you can create a so-called pull points. So sometimes if you need to extract the watershed, so-called upstream watershed. So look at this one. I'm going to maybe come here and just to show you. Assume that right now you're doing some hydrological analysis. You want to figure out where the water coming from. What's your upstream? So upstream means water going to contribute to your area. So in that way, for example, let me just come here. Let's say, okay, I'm going to walking in this area. And now I want to figure out, for example, in this river here. And you might be wondering, where does this water coming from? Where's the upstream water? Like where's the so-called watershed in your upstream? So what you can do is that you can come to the map and you can find a certain location that you like. And then we can ask Whitebox to delineate your upstream watershed for you. So I'm going to use this one here. Maybe I can place a marker somewhere here. So for example, okay, I want the water. I've maybe set up a gauge in here. And then I want to figure out how much water is coming through here. Where are they coming from? So I place a point here. Then you need to run this tool called snap a pull point. So if you can either use to drop a marker or you can just specify the exact latitude and longitude. So for this one, I'm going to just run it. And it's going to use the one that I just draw on the map. And after that, you're going to snap pull point means sometimes if you accidentally place the point that's not perfectly along the river, you can snap the pull point so that you can delineate the large watershed. So it makes it better. So let's add this one to the map. And I will show you. Right now, we have snapped the pull points. So take a look. So what this one is doing? So originally, I put a point in here. And this point actually not exactly along this major flow accumulation line. So you can set a threshold, for example, 300 meters. It's going to snap this pull point to the main river line. So in that way, you're not offset, right? So for example, that's like, you're driving on the highway. Make sure you're driving on the highway, not driving on the shoulder, right? So this is moving you to the main road so that you can figure out where the water is going to come from. So this is so-called the snap pull points. So this point is where the water pull point means water is going to pour into this location. So once you have this, you just run the next couple lines. Then let's see. Okay. Delineate the watershed using the watershed tool. And we need the flow direction. We need the pull point. And then you're going to output the watershed. So run this one, and then convert. You see? So now we have this watershed. It's going to be just a raster, but then you can convert that one to a vector data set. Again, it's still loading, but maybe let me run the final step. Convert the raster to vector, and then load the vector on the map. So the vector should load faster. See that? See this yellow color? This is basically the upstream watershed. So all the water coming from here, eventually going to pass through this location. So passing through this outlet. And this is exactly how you figure out your upstream. Where's your upstream? Where's your contributing area? Sometimes it's also called catchment. Catchment means like where the water, if there's rainfall coming into this watershed, eventually going to flow from upstream to downstream, and at some point, it's going to pass to this location. Right? So you see here, it's exactly along this main, the river, the streamlines in here. And this is how you do some simple hydrological analysis using leaf map and white box tools. Is it easy? Right? Pretty easy. So now you know like how some of those hydrological data sets are derived. All right, so that's about the hydrological analysis. We only have a couple minutes for the LiDAR data. I want to quickly show you. It's not the focus, but you can certainly, there are a lot of LiDAR tools available in WhiteboxTools. So let me quickly show you. I'm going to use WhiteboxTools. I'm going to download a sample LiDAR data set, and then you can use the leaf map to read the LiDAR data set as a large format. You will need to make sure you install the packages at the beginning, and let's see. Okay, download is done. Then I can read this one as a large format data set. So LAG basically a compressed LiDAR data format. And this one to show you, for example, the metadata. What's the version? For example, this is a LiDAR large format 1.3. The latest one is 1.4. So we can convert this one to the latest one. And then you can show, for example, the version right now, this is 1.4. Then you can write this one, basically export this one as the latest version, and then save it as .last. So .last is not compressed, okay? .lag is compressed. So now with this one, we can do the data processing. The reason why we need the last format is because some of the tools, the white box only handle the last format, okay? And you can run this one, LiDAR histogram. So it's going to generate a file, an HTML file on your computer. You do need to open this one locally. So it should be somewhere here, like histogram HTML. If you open it up, oops, not supposed to open this one. Let me change this quickly. Open in the browser. So basically, this is just histogram showing you the elevation values within this LiDAR DM. So just the histogram, so you can see that overall what's the pixel ranges, the value. And after that, we can start quickly do some analysis. We can view the LiDAR data. So the view LiDAR data basically shows you how to visualize the LiDAR data in 3D. And this might be a little bit slow, depends on how big is your data set. And look at this. So this would be the LiDAR point cloud being rendered here within this one. It's actually 3D, but it's maybe a little bit slow because you might need a GPU like faster, but you can certainly see, is it moving? You can rotating, you can turn it around. It doesn't work very well right now on my computer because it's using a lot of GPU. So GPU is much faster, but you can certainly rotating, zoom in and zoom out. If your computer has a GPU, that should be better. But at least right now you can quickly visualize the LiDAR point cloud within Python. You see, it's very slow, just like a sloth waiting to respond. But anyway, I'm going to stop this one because it's way too slow. And so next we can do the elevation slicing. So sometimes if your LiDAR data and the LiDAR data have some artifact, for example, you have some airplane or something accidentally being captured in your LiDAR, you're going to have some like outlier of very high elevation. So you can set up, for example, the minimum, the maximum, and then you can remove, filter those out. And after that, you can view it again. I'm not going to view it. It's already removed. So I know it's going to be slow. And then you can just call LiDAR digital service model. It's going to construct the elevation based on the LiDAR point cloud, just using one line of code. So this might take a couple seconds. But if you ever created LiDAR point cloud yourself, you want to construct a DM based on a LiDAR point cloud, this one can help you. Otherwise, you might need to pay some commercial software in order to utilize this one. And not so bad, it's so slow. Not B. Okay, 27 seconds, not bad. And like I said, sometimes if it means the coordinate, you might need to add it. So this one, you do need to know what's the coordinate system for your LiDAR data. Once you have that, then we can create the DM. So take a look. So this will be your LiDAR digital service model. Basically, it contains everything. about the DM, right? So this has trees, has buildings, have everything in there. And it's so-called a digital service model. And commonly, sometimes we need a so-called bare or DM, right? So this is a very high resolution. It might take some time to load up. And you can remove the so-called terrain object, remove all the buildings, remove all the trees, and then you can create a so-called bare OSDM. And if you subtract the DEM from the DSM, then you get the height. Basically, you can get like how high does each pixel, a trees, building, or something like that. And again, you can try it out. There's only a couple more lines. So after that, you should be able to create 3 data products out of this LiDAR point cloud. Is it still stuck? Okay, something wrong with my voice call. Anyway, so try some of these tools after class and see how it works. You can input any LiDAR data, create your own DM, create your own DSM, and then you can use the DM, for example, to do some hydrological modeling. So just like what we covered in the previous section. So I think we only cover maybe 10, 15 tools. There are over 500 tools. So you can do a whole lot more things if you want to. Again, so all free, open source, and it's only very tiny. This is gonna just like 20 megabyte compared to you install a desktop GIS, 2 or 3, 4, 5 gigabyte. It's gonna take a lot more space, okay? And I hope you can use some of this in your final project. Utilize some of the new tools to do some analysis for some of your own projects. Okay, so